Before starting today's class, first I will summarize chapter 8 for you. Using this slide. This slide will help us summarize the whole chapter so far. In this slide, as we can see, that we start with working with a numerical population on a random variable x. We have a population on x. This population is modeled by a density function or a mass function, depending upon if x is discrete or if x is continuous. This mass function or density function has some unknown parameters, for example, unknown mean, unknown variance, and sometimes we are interested in estimating those parameters. So for this chapter, the interest is in the unknown parameter mu. So this is actually the story. The first line, you have a population. This population is modeled by a density function, and this density function has unknown parameter mu. To estimate this unknown parameter mu, what do? You take a sample. From this sample, what do? You compute x bar, and you call this x bar to be a point estimate of the unknown parameter mu. Then you say we don't stop at the point estimate. We do not stop at the point estimate. We add something to the point estimate, we subtract something to the point estimate, and that point estimate becomes an interval estimate. So the something that you add or subtract is called a margin of error, right? So you convert the point estimate into an interval estimate using your knowledge from chapter 7, using the sampling distribution concept from chapter 7. And after you convert, you come up with two cases. The first case is when you are interested in mu, but the side parameter sigma square is known. If it is known, you use z-based interval. If it is unknown, you use the t-based interval that uses the sample standard deviation instead of the population standard deviation. And the third case, I will discuss it today when I take you to the t-table and show you the limitations of the t-table. Now, in the previous class, we did solve a couple of examples from Z case. We had this example. In this example, we solved for the confidence interval, 95% confidence interval. We did 99% confidence interval. We did the estimation of sample size such that the width of the interval or the margin of error is fixed. We did all of that. Today, we will move on towards the confidence interval for mu when sigma is unknown. As we discussed in our previous class, when sigma is unknown, you replace it by its counterpart from the sample, which is the sample standard deviation. When you replace it by the sample standard deviation, we said that the resulting distribution is no longer z, it becomes t. And when you replace this t into the confidence interval formula, the confidence interval formula becomes this, where sigma is replaced by s and z critical value is replaced by a t critical value. Now, the thing about this t table or t critical value is when you have to go to the t table and look for the critical value, unlike z, you don't have to look for only alpha by 2 or 1 minus alpha by 2. You have to look for alpha by 2, and you also have to look for the sample size, n minus 1, the degree of freedom for the t distribution. So let me show you the t table, and I will show you how to look for a critical value from the t table. It is much more easier than the z table. For the z table, we had a 4-step procedure. What was the 4-step procedure? In the question, you are given 1 minus alpha. Let us say 1 minus alpha is given to be 0.95. What do? The second step, you find alpha. So alpha is 0.05. What was the third step? You find alpha by 2, which is 0.025. What was the fourth step? You find 1 minus alpha by 2. Why 1 minus alpha by 2? Because the z table is given in less than form, and you have to look for the upper tail area. And to look for the upper tail area, you take the complement in terms of 1 minus. So 1 minus alpha by 2 is 0.975. Then you go to the z table. You look for this value 0.975 inside the z table. And the corresponding value of z, you call it 0.025, z alpha by 2. And this, I think, was 1.96. This was a 4-step procedure to look for a critical value in Z table. Now look at this whole procedure. Is sample size involved anywhere? No, this will not be the case with T, because now you are estimating the standard deviation through the sample. It will matter how big is your sample. So the critical value will take into the account the sample size through another parameter which is called degree of freedom for T distribution. And this degree of freedom is a function of sample size. It's n minus 1. So let us continue to solve a question. And when it comes to the critical value, I will take you to the T table. Look at this question. This is the question that we were solving at the end of the previous class. In this question, we have a materials engineer tests 15 specimens of a new polymer, and the tensile strength of these 15 specimens, they are given. The values are given. Assume normality, but the variance is unknown. Now, this statement will not be in exam. The variance is unknown. You just have to see the question and you have to see that the variance is not given. If it is not given, of course, it is unknown. Construct a two-sided confidence interval for the mean strength. In the book exercises, if anywhere you see a one-sided confidence interval, that is not in your syllabus. Remember, one-sided confidence interval is not in your syllabus. Only two-sided confidence intervals are in your syllabus. Now, what do you do with this data set? The first thing you do, if you look at the formula for a 95% confidence interval for mu when sigma is unknown, the formula is something like this. From this formula, you have some of the unknown things that you need to find from the data. The first thing is the mean of the sample, the standard deviation of the sample, the size of the sample, and ultimately the critical value. Once you have these 4 things, you can just plug them into the formula and get the confidence interval. To get these things, the first thing I will do is I will find the sample mean and the sample standard deviation. I know the sample size is 15. So I need the mean and the standard deviation. To find the mean and the standard deviation, you will go back to chapter 6, use the formulas of chapter 6. I will try to find it from Excel. You got it already? Metallic. Are you sure it is correct? What is the mean? Correct. Now you can say, I'm sure it is correct. 1.9072. So the mean is, we found it from the sample. The mean is 61.18, and the sample standard deviation is, was it 1.9072? Yes. Once we have the mean and the standard deviation, then we go to the T table to get the critical value. To get the critical value, you need 2 things here. You need alpha by 2 and you need V. Now, the thing about T table, I will show you the diagram at the top of T table also. The difference between T and Z is you don't need to do this last step. that you did in Z. You don't need to do 1 minus alpha by 2. Why? Because Z is given in less than form, T is already given in greater than form. The area under the curve for T table is also upper tail area. It's not lower tail. For Z, it was lower tail. To convert it to upper tail, you did 1 minus, last step. For T, you don't need to do this last step. Just directly go to the T table and look for alpha by 2, number 1. So I will find alpha by 2. For this question, my alpha by 2 is what? 0.025. What is my V, which is n minus 1? N is 15. So V is what? 14. Now I will go to the T table and I will show you how this T table looks like. And we will look into all the components of T table. There are two major differences in Z table and T table. Okay, look at this Z table first. Look at the two diagrams. Where is the highlighted area? Towards the left side or towards the right side? Left side, which means the lower tail area is given to you. In the Z table, lower tail area is given to you. That's why you were converting it to upper tail area by doing the last step, 1 minus alpha by 2. Number 1. Number 2, what is at the edges of the table? Is it the value of Z or the probability? The value of Z. What is inside the table? The probability or the value? Probability. These are the two differences in Z and T. In T table, the area will be number 1, upper tail area. Number 2, you will be given the probabilities at the edges and the values of T will be inside the table. Opposite. Here, the probabilities are inside the table and the values are at the edges. There, the values will be inside the table, probabilities will be at the edges. So now I will show you the T table. Let me show you only the left side with small degrees of freedom. The right side is nothing but the comprehensive degrees of freedom. First thing you look is this diagram. Look at the diagram. Where is the highlighted area? Upper tail area. That means you don't need to do that last step. Just look for alpha by 2 in the table, not 1 minus alpha by 2. Where are those alpha or alpha by 2 given? They are given in the top row. Only few values are given, unlike Z table. There were all the values from almost 0 to 1. Everything was available. Remember? But here only few values are available. What are those few values? 0.0005 is available. 0.001 is available. 0.002 is available, and all the way up to 0.4. Only a few values are available. Not like Z table, which was comprehensive for all the probabilities, starting with 0.0000001 all the way up to 0.99999. That was much more comprehensive than this one. Only, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 values are available for T. Then, where is the degree of freedom? First column. So for your question, what was the degree of freedom? 14. You will go into the first column and look for 14 degree of freedom. What was alpha by 2 in your question? 0.025. So look for alpha by 2 here, 0.025. Much easier as compared to the Z. Look for the degree of freedom here. Look for alpha by 2 here. And the corresponding value is your critical value, 2.145. That's it. Much easier than Z table. This is much easier than Z table. You don't have to look a lot into the table. Just look at the degree of freedom in the first column and look for alpha by 2 in the first row, and the corresponding value inside the table is your critical value. So in this case, your critical value is this value, 2.145. What if I asked you for a 99% confidence interval? What would be the critical value for a 99% confidence interval? Yes. Yes.
2.977.
2.977 would have been the critical value. This 2.977 if I had asked you for 99% confidence. But if I ask you for 90%, same sample size, 90% means alpha by 2 is 0.05. So you go down, 1.761 would be the critical value. So we take this critical value from the T table and we put it here. T alpha by 2 with V is 2.145. And finally, it's just the plug-in. You plug in the values. The confidence interval is 61.18 plus minus 2.145 times 1.9072 divided by square root of 15. And that's it. You get a lower limit, you get an upper limit. How do you interpret this lower limit and upper limit? Exactly the same like Z. You will say we are 95% confident that the true, what was the variable? The true mean tensile strength is between this and this, whatever is the lower limit and whatever is the upper limit. Again, I repeat, you will not talk in terms of probability. You will not say that the probability that mu is between this and this is 95%. After constructing the confidence interval, the concept of probability is not applicable. We will not talk in terms of probability. Any questions up to this point? This is much simpler than looking into the Z table. So another point, I will come to that point later. This question, construct a 99% confidence interval. What will be the difference? Just the critical value will be 2.977. So this will be 61.18 plus minus 9072. And the critical value was 2.977. Will this be wider or narrower than 95% confidence interval? Wider. And it makes sense because if you want to be more confident, you have to be on the safer side to give a wider confidence interval. And we are done. Now, what if I give you a question where the sample size is 384 and sigma is unknown? Sample size is 384 and sigma is unknown. What will be the degree of freedom? N is 384. What is n minus 1? 383. Now, when you go to the T table, you will see that only a limited number of degrees of freedom is available. They are available up to 50 on the left side, but there is more to the right side. They are available all the way up to 100. After 100, they are available in gaps, but up to 250. If your sample size is more than 251, the degree of freedom will not be available in the T table, right? It will not be available in the T table. In that case, what do you use? You use this information. When we introduced the T distribution, we said something here. Read this. We said as the degree of freedom increases, T distribution approaches what? Z distribution. So in case you have a situation where your sigma is unknown and the sample size is too big and you don't find the critical value from the T table, just borrow the critical value from the Z table. And that's it. Just replace it by the critical value from the Z table and continue with the confidence interval. And this kind of confidence interval is called large sample approximate confidence interval for mu, where you replace the T constant by a value from the Z table. That's it. So in case your sample size is too big, this is not a third case. There are only two cases. Sigma is known, sigma is unknown. Now this is a limitation of the t-table. It's not a case. It's a limitation of your t-table that it doesn't give you the comprehensive degrees of freedom. So because of that limitation, you come up with a solution, and the solution is you plug in the value of t corresponding to v equals infinity. Z distribution is actually a t distribution when the degree of freedom is infinity. So the last row in the t table, look at this last row in the t table. This one, this is against v equals infinity. These are critical values from the z table, if you remember. You remember this 1.96? This is against 95% confidence interval. You remember this 2.575 between 2.57 and 2.58? You remember this 1.645? These are actually from the Z table. So in case the degree of freedom is too large and the samples, the population standard deviation is unknown, you use the t-based interval, but just replace the t critical value by the Z critical value. And this is where we summarize this whole concept here. Now, this is the whole summary of your 80% of the chapter. You have an unknown population on a random variable x with the density function f of x with unknown parameter mu. You want to estimate this unknown parameter mu, you take a sample. From the sample, you compute the sample mean. Now, you don't stop at this sample mean. You don't stop at chapter 6. Point estimate is not enough. You go one step further. From this point estimate, you try to compute the interval estimate. You try to compute a 1 minus alpha into 100% confidence interval for mu. But when you go into this discussion, you come up with two cases. Whether the side parameter is known or unknown. If the side parameter is known, you use the z-based confidence interval, and here is the formula. And if the sample size is unknown, you use the t-based confidence interval, and here is the formula. Now, within this t-based confidence interval, you have a limitation. What is the limitation? If the degree of freedom v is not available in the t-table, you just replace this critical value by a critical value from the z-table, and you proceed with the confidence. And one extra thing that you did in the previous class was the estimation of sample size when the margin of error was fixed at some point E. This is only for the left side case when sigma is known. This estimation of sample size is not with you in the syllabus when sample size is unknown, so you will not see it here. The estimation of sample size will only be covered towards the known variance side. This is the summary of confidence interval for mu in one slide. Any question from this summary? I'll use exactly the same summary for the next topic. So look at this summary and make a map of this thing in your mind. Using that, can we solve this question? By the way, this is how the question will come to you in exam if it is from a confidence interval. Usually in exam, we don't give you the sample. We give you the summary of the sample in terms of summation x and summation x squared. Usually, most of the situations you will see that sample will not be given. Summary of the sample will be given. So from this summary, can you find x bar and s? Yes, you just have to plug in these numbers inside the chapter 6 formulas to get x bar and s. So why this question is there? Because of sample size. So how do you compute the confidence interval in this question? You get x bar, you get s, okay, and then you plug it into this formula. Why I'm writing z alpha by 2 here and not t? Principally, there should be t here, but why am I writing z here? Because of, let me write t and then borrow it from z. So the value you will get from the z table, Let's practice one more time. How will we get this value from the Z table? What is alpha? 0.1. What is alpha by 2? What is 1 minus alpha by 2? We will go to the Z table, look for 0.95 inside the Z table, and the corresponding value at the edge of the table will be Z alpha by 2. So let's go to the Z table and look for 0.9500. 0.9500. Keep an eye on 0.9500. Where is 0.9500? Do you see 0.9500? It's in between these two values, correct? And it is almost in the middle of these two values, right? So I will take the middle of 1.64 and 1.65. What is the middle of 1.64 and 1.65? 1.645. And if you go to the T table and look for the same value with infinity degrees of freedom, because alpha 0.05 is a popular value, you will also find it from the T table. Go to the T table and go to the last row, infinity degrees of freedom, and look for 0.025. You see this value? Where alpha is 0.05, sorry. Total alpha was 10%, so alpha by 2 was 5%. Go down to 5%, and you will find this value here also, 1.645. So this last row is actually few very limited values from the Z table, only few of them. The Z table is more extensive. You will find all the probabilities, but here only for few probabilities it is available. Any questions so far? No questions so far? Okay. Now keep this summary in mind, and I will extend this summary to the next situation. This is completely new topic. Here, your population was numerical. There were numbers, either discrete or continuous, there were numbers. What if your population is binary, true or false? Yes or no? 0 and 1. Not categorical, even one step further than categorical, just binary. You are interested in one of the categories and the remaining categories are all failures. So if your population is binary, here we are. You have a binary population and the values of the variables are 0 or 1, true or false, yes or no. And you are interested in proportion of true. Initially, I was interested in the average score of first major exam. X was the score in major exam. Now I'm interested in whether the student passed or failed. So Y is either pass or fail. And I'm ultimately interested in the proportion of students who passed the exam, P. P is unknown parameter. In my population, there are infinite many elements. Some of them are true, some of them are false, and the proportion of trues is P. And I don't know this. This is an unknown population parameter. The proportion of successes in my whole population is unknown. Correct? To estimate this unknown, what do I need to do? The same story. I will take a sample. I'll have a sample of trues and false. Correct? From this sample, I will estimate the proportion of successes from the sample using the formula number of successes divided by the sample size. So let's say I selected 50 people. Out of 50 people, 10 of them were successes. So my proportion of successes will be 10 divided by 50. So this P hat, which is the number of successes divided by the sample size, will serve as a point estimate for P. Step number 1. Step number 2, you need to convert this point estimate into an interval estimate. And to convert this point estimate into an interval estimate, again, you will add and subtract something. That something is called what? Margin of error. Correct? You will add and subtract something. that something is called margin of error, P hat plus minus margin of error. And that margin of error again comes from chapter 7. We did not cover P hat in chapter 7, but again from the sampling distribution concept, that margin of error comes out to be, this. A critical value from the Z table multiplied by the square root of P hat into 1 minus P hat over N. This is the margin of error. And this is the formula for 100 times 1 minus alpha percent confidence interval for the population proportion when the population is binary. Then the second task is, again, like we did for the numerical population. What if you want to estimate the sample size for a given value of margin of error? Again, you will just plug in the values and get the sample size. And at the end, what will you do with the sample size? You will round it up or round it down. Always round it up because the equality is greater than equality. Then there will be another third case for the sample size estimation, which I will come to that one when I'm discussing the example. So let me go to the example now. Here is the example. Read the example carefully. The example says that the US Postal Service, they have used optical character recognition since 1960s. And in 1983, the technology was deployed to major postal offices throughout the country. In a random sample of 500, now the important information. In a random sample of size 500, this means your N is 500. 466 were read correctly. How many of them were successes? 466. What is the proportion of codes that were read correctly? Calculate. 9. 3, 2. Now, if I ask you a question, give me an estimate for the true proportion of the codes which were read correctly. The point estimate is 0.932. So you can say that 93.2% of the codes, they were read correctly by this optical system, whatever optical system was deployed by the US government. But they are not asking for the point estimate. What are they asking for? Interval estimate. How much interval estimate? 95% confidence interval estimate. So for this one, again, you need number 1, sample size, number 2, P hat, number 3, critical value. I will write the formula again for you here. The formula is P hat plus minus a critical value, P hat 1 minus P hat over N square root. So you need P hat, you need N, and you need a critical value. You have N, which is 500. Now you have P hat, which is 0.932. The only thing you need is now the critical value. For this, again, go to the Z table, looking for the value of 1 minus alpha by 2. 4-step procedure. What was your alpha? What is alpha by 2? What is 1 minus alpha by 2? Look for this value inside the table, and the corresponding value will be your value of Z, which is 1.96. Now plug it into the formula, and your interval estimate will be 0.932 plus minus 1.96 square root of 0.932, 1 minus 0.932 over 500. This will give you a lower limit and an upper limit. And what can you say about this confidence interval? You will say that we are 95% confident that the true proportion of correctly read codes is between this and this. Between this and this, whatever the two numbers come. Compute it for me, the lower and the upper limit, and I will write it for you. We're almost done with the chapter.
0.954. This is the lower.
This is
the upper.
upper.
Would be 0.909.
So we will say that we are 95% confident that the true proportion of codes correctly read by the optical machine is between 0.909 and 0.954. Now, in case you encounter a question where this limit is more than 1, you will make it 1, because the proportion cannot be more than. Can the proportion of something be more than 1? It cannot be more than 100%. So in case this is more than 1, you will replace it by 1. In case this is less than 0, you will replace it by. Can the proportion of something be less than 0? No. So in case this goes out of 0 and 1, you will replace either the upper limit or the lower limit by the corresponding, either this one by 0, or one of them will happen in some cases. Either the upper limit will exceed 1 for some cases, or sometimes the lower limit will go beyond 0. So if that happens, you replace it by 0 and 1.
Does it indicate miscalculation?
No, it doesn't indicate the miscalculation. It indicates that sample size was not big enough. It doesn't indicate a wrong calculation. Even with the correct calculation, you might have a value of lower limit to be less than 1. Last question. What does it say? Assuming that the point estimate P equals 0.932 from part 1, determine the sample size required. What is required? N is required. To achieve what? Margin of error is given to be what? 0.021. And the confidence level is what? Now I will summarize the whole information. The first thing which is given to you is you need to determine N, starting from the statement. Then it is given to you that P hat is. Then it is given to you that E is. This is where many of you will make mistake and read this 2.1 as 0.21. 0.21 is 21%. 0.21 is 21%. 2.1% means 0.021. Some of you will read it as 0.21. This one. This is not 0.21. This is 0.021. Then the next piece of information which is given to you is alpha, which is. Now you go to the formula sheet, and the formula sheet will give you something like this. It will give you the confidence interval for P. And next to the confidence interval, there will be a comma, and the formula sheet will give you something like this. I don't know if they use greater than sign or equal sign. It will give you Z alpha by 2 over E whole square P into 1 minus P. To estimate the sample size, you need what? You need a critical value from the Z table. You need the margin of error. You need an estimate for the P. They gave you all of that. They gave you an estimate of P to be 0.932. They gave you the margin of error to be 0.021. They gave you Z alpha by 2 indirectly through alpha. They gave you alpha to be 5%. You can find Z alpha by 2 from there. So go ahead and find that your Z alpha by 2, what is Z alpha by 2 for 5%? 1.96, plug it into the formula. When you plug it into the formula, you get N to be greater than or equal to 1.96 divided by 0.021 whole square 0.932 times 1 minus 0.932. 577, I guess.
5.
552.
75.
So what should be n in this case? 553. Remember, 553. Remember, round it upwards. Remember. I'll tell you something that is senseless in this question, which will not make sense in this question. And from there, I will generate the idea for the next concept. Usually, why do we estimate the sample size? When do we estimate the sample size? We want the margin of error for the constructed confidence interval to be within range, so we want a sample size. After calculating the sample size, we will select the sample of that size. What will you do with the sample? Look here in this diagram. You have this population. From this population, you have to select the sample. And to select the sample, you need to know what is the sample size. Correct? So sample size is needed before this one, right? You're somewhere here, you have a problem in your mind that you have a population. From this population, you want to estimate P and you want to construct a confidence interval and you want the margin of error to be within this. And now you are planning to take the sample. And before you take the sample, you will estimate the sample size, correct? So you are at this stage. You don't have the sample. If you don't have the sample, do you have this P hat? Where will P hat come from? From the sample, and you don't have the sample yet. You are at the stage where you're trying to estimate the sample size. Now, in this formula of estimating the sample size, where is that formula? In this formula of estimating the sample size, you are estimating the sample size for this guy, right? And you need this guy for estimating sample size. Conflict. You need n for P and you need P for n. What is going on? When they gave us in the question that P hat, when they gave us in the question that P hat is 0.932, isn't it impractical? Isn't it impractical to assume that P is 0.932 when we don't have the sample yet? We don't have the sample yet. Where did we get this 0.932 from? How did it assume? So usually in practical life, at the stage of estimating the sample size, you don't have this estimate. Usually, in some cases, you have from the previous year, somebody did the study and they have an initial estimate of P. Suppose I want to estimate the proportion of students who are interested in data science. So suppose last year somebody did the same survey and from last year somebody has the estimate of proportion of students who are interested in data science. So we can use that. But in more practical situation, this is not available. If this is not available, to be on the safe side, you will select a sample size that maximizes the value. To be on the safe side, you will select a maximum sample size, a bigger sample size to be on the safe side. And what is the value of P that maximizes this sample size? What if you put 1, that will be 1 minus 1, 0. It will minimize, not maximize. If you put 0 again, this will be 0 and this whole thing will be 0. It will minimize, not maximize. 0.00001 will take it close to 0. 0.5. 0.5 is the value of P that will maximize this whole thing. Where does 0.5 come from? Math 101, differentiate this function and put it equal to 0. What is the function? P minus P squared. Differentiate the function. Take the first derivative, put it equal to 0. What is the value of P you get? So to be on the safe side, if you don't have any guess about P, the best value of P to plug in to be on the safe side that maximizes the sample size is 0.5. And that is your next part here. Read the next part very carefully. There is no calculation, we'll just plug in. Determine the sample size required to ensure that the margin of error is at most 2.1%. for a 95% confidence interval, look at the last statement. Regardless of the true value of P. In this case, what will you do? Your N will be greater than or equal to 1.96 over 0.021 multiplied by 0.5 into 1 minus 0.5. So if there is no prior estimate of P available, what is the value of P you will use in the formula? 0.5. And again, you will round it up. Again, you will round it up. Again, it is square. Yes, it is very good that you identified. Bonus. You were paying attention, so I will give you bonus. 0.0000001%.
217. 217.
217.
Right.
Exact value.
7.77.
2177.7778. What will it become? 2178. And this is the end of chapter. Here is the summary of the chapter. We talked about confidence interval for mean. We talked about confidence interval for proportion. For the confidence interval for mean, there were two cases. When sigma is known, when sigma is unknown. For the confidence interval proportion, there was only one case. No case, it was large sample. For unknown case here, we encountered a problem where the degree of freedom was not available in the T table. We use Z for the large degree of freedom in this case, and that's it. Formulas were given to us for estimation of sample size for mean, also for the proportion. Two different formulas are given to us. We need to use those formula. For the proportion, there were two cases in the sample size estimation. Either the prior estimate for P is given to you or it is not given to you. If it is not given to you, you use 0.5 as a prior estimate for P.